Hello everyone, I welcome you all in this lecture. So, in this lecture, we will be talking about washout filter and beta control loop analysis, and that comes under the directional autopilot design and analysis. So, I request you go back to my course flight control system design, conceptual and practical design playlist and see all the lectures so that you can connect this lecture with the previous one. Okay, so today topic is washout filter and beta control loop analysis. So in beta control loop, already I have told you, you have to control beta using PI controller, and the feedback you will take as a beta, and you will command beta as a 0, and the PI will try to control the beta equal to 0, and the transfer function will be beta by delta r, and with the actuator dimension r. So already I have told you the significance on all this. Okay, now you can see how the beta control loop with washout filter look like. Okay, so you have to take a extra feedback here, which is yaw rate. All other things remain same. Beta you will command 0, and beta you will take a feedback. Ki beta is an integral gain. Kp beta is a proportional gain that is used to improve the performance. Compensator is there, tau a plus 1 divided by tau b plus 1 in order to modify and to improve the response. Okay, rudder actuator dynamics first order we have taken. If you don't know the actual actuator dynamics, you can actually consider as a first order dynamics, and you have to obtain a transfer function beta by del r from the nonlinear ecosystem of motion, linearize and then convert it into the Laplace domain and find out the beta by del r. That already these things I have told you in the previous lecture in this flight control system design course. And sensor dynamics you have to include. If you don't know, you can take a first order. Okay, and together rudder actuator dynamics, sensor and beta by delta r together it is called plant. Okay, so here you can see there is a ADU filter, air data unit filter. So in this filter, what is the purpose of this filter is to remove the noise and all in order to provide a smooth beta. Okay, so generally ADU filter consists the angle of attack, side slip angle, velocity, dynamic pressures, static pressure, etc. Okay, so here we are taking the interested in beta, so that is why we are taking the feedback from ADU filter. Okay, now here you can see that first the yaw rate has been taken, which passes through the rate filter, but means in order to remove the noise, and then passes through the washout filter. So washout filter name itself implies something is going to, some signal is going to block. Okay, so here the low frequency signal will block and high frequency will passes. So you can say that washout filter is also known as a high pass filter. Okay, and then in order to further improve the damping, you can multiply by the kpr gain and all. Okay, and washout filter you can write as a ks divided by s plus a, where a as example here I am taking 0.3 and k is 1. For a, when you do the analysis in any other software, simlink and all, actually you can change this a value and k value in order to see the response, different kind of response, and based on your requirement you can pick one. So why actually this washout filter needed, and how, where it is placed actually, and is there any kind of aircraft which is using this kind of filter and all? So the answer is yes. You might have familiar with the aircraft Boeing 737 and all other series and all. So we'll see the rudder part. In rudder part there is a vertical tail part, and there is a control surfaces associated with the vertical tail is called rudder. Okay, so in rudder you can split into 2-3 parts. Okay, so one portion is you may utilize as a damper, like for example yaw rate damper. You will not deflect complete rudder, but part of the rudder you will deflect as a yaw damper. Okay, so in the yaw damper this washout filter is used. You can understand in this way, for 20% of the complete rudder or 30% of the complete rudder, you may utilize as a yaw damper, and in that yaw damper there will be washout filter sitting. Okay. More, if you go more in depth, so in aircraft lateral case, there you have a three mode: Dutch roll mode, roll, pure roll mode, and spiral mode. So generally spiral mode are very slow. In majority of the cases, it is unstable. It is generally lie right half the plane close to the origin. But in a closed loop using PI controller feedback, if you are closing the loop, that means final when you close the feedback and you will do the stability of a closed loop, then you will find the spiral mode is also stable, because see, already I explained to you, you can have a pole unstable in open case but cannot be in a closed loop case. So in closed loop case, all the poles should lie on the left half of the plane. Okay, let's say you have done it beautifully, but it may be more far from the origin. That means you have stabilized more. So that is also when the pilot will fly, that is the pilot will not like this kind of flight, because it is too much stable and spiral mode is already slow. So it's taking turn and bend slowly. Okay, so that is again the problem. So actually you can eliminate this problem by using washout filter. Okay, and another scenario you can consider is particular. You have hit with the strong gust on the vertical tail, and so washout filter will try to pass out this signal, and it will try to compensate this. And let's say you are taking coordinated turn, okay, where you do not want this kind of I mean to say uh, washout filter. Okay, so generally the use of wash filter, I already told that when there is a gust hit with the vertical surface, one example, then you will use washout filter. So what about the standard case where you are taking a coordinated turn? So in that case, washout filter will block the signal. So that is the beauty of washout filter, you can see. Okay, so here already what so far we have discussed that design trim condition. So in that design trim condition, we have found out the transfer function without delay, with delay, with actuator and sensor, beta versus delta open loop, beta versus delta R, and the beta versus beta commanded open loop, and the beta versus beta commanded closed loop. You can see the transfer function table I have put. Okay, now I'm doing the beta control loop analysis. Okay, so now in this case, what I have given, so already I told you what example aircraft I have considered in the previous lectures. Okay, and what trim condition we are testing this controller. Okay, so what I have commanded 360 degree. Okay, so 0 to 360 degree sweep. Okay, with approximately 3 degree per second side out. Okay, and you can see here the controller is trying to achieve the performance perfectly, and you can see that at an initial stage, in order to take a turn, you have a bank, and finally when it is reaches to 360 degree, the bank angle becomes 0. That means you have to take a bank in order to take yaw, and once you achieve 360 degree, and you may level the flight. Okay, so like that it is happening here perfectly. Okay, so in order to attain the bank, you need to deflect the aileron. That is also you can see in the figure. And when this aileron is deflected, and there will be beta generated, in order to counter that, you have a rudder deflection also. Okay, and you might have observed that I have plotted delta A dot and delta R dot. That means how fast the aileron is working and how fast the rudder is actually required and working. Okay, roll rate and yaw rate also you can see. So I hope the purpose of beta control loop and washout filter you have understood. And if you don't have any problem, have some suggestion, then also you can put on the comment section. And if you have any problem to understand this, please ask us. We will try to explain in a very effective manner, and will try to provide all the necessary source to you. Okay. And as of now I'm building a fundamentals concept, why it has been, why washout filter is used, and what is the difference between beta control loop and washout filter separately, and why we need washout filter in a beta control loop. And I am try to show you the results also, uh, using the example aircraft, example trim condition and all. And in future classes I will try to implement this washout filter in front of you also. As of now I am showing the result only, but in the model loop simulation classes I will try to implement this washout filter, and I will try to give you more significance, and will try to relate our understanding more closely, and will try to learn more from those upcoming lectures. Thank you so much.